Good morning, everyone. Today, we will explore the foundations of heterogeneous programming through chapters 1 to 4 of Data Parallel C++. These chapters introduce SYCL and DPC++, explain where code executes, examine how data is managed, and show how parallelism is expressed. Our focus is not only on understanding SYCL syntax. We will also consider the engineering decisions behind device selection, memory management, kernel organization, correctness, and performance. These foundations will prepare you for more advanced topics such as parallel algorithms, profiling, optimization, and heterogeneous system design. Modern computing systems rarely depend on only one type of processor. A system may combine a CPU for control-intensive operations, a GPU for high-throughput parallel computation, and specialized accelerators for particular workloads. Each architecture has different strengths, so the main engineering challenge is deciding which processor should execute each part of an application. Heterogeneous programming models such as SYCL help us write portable C++ code for these devices. However, portability alone does not guarantee performance. We must still understand the workload, memory behavior, execution model, and hardware characteristics. By the end of this presentation, you should be able to explain the purpose of SYCL and its relationship with DPC++ and OneAPI. You should also be able to describe the host, device execution model, discover available computing devices, and justify the selection of a CPU or GPU for a particular workload. From the data management perspective, you should be able to compare unified shared memory with buffers and accessors. Finally, you should be able to express parallel work using range and ND-range kernels and evaluate basic performance and correctness considerations. In a sequential program, operations are generally performed one after another. If a problem contains many independent calculations, this approach may leave much of the available hardware unused. Parallel programming divides a computational problem into smaller units that can execute concurrently. For example, the elements of a large array may be processed independently. Parallel execution does not always guarantee a shorter execution time. Kernel launch overhead, memory transfer, synchronization, and workload size all influence performance. Therefore, parallelization should be based on the structure of the problem and supported by measured performance evidence. SYCL is an open, cross-platform programming model developed by the Kronos Group. It allows heterogeneous applications to be written using modern C++. A SYCL program normally contains host code and one or more kernels. The host code manages the application, while the kernels execute on a selected device, such as a CPU or GPU. DPC++, which originally referred to Data Parallel C++, is Intel's implementation of SYCL within the OneAPI ecosystem. Although DPC++ may provide additional features, the fundamental programming model follows SYCL. In this course, we prioritize current SYCL 2020 terminology and programming practices. This code illustrates the basic structure of a SYCL application. We begin by including the SYCL header and creating a queue. The queue is used to submit computational work to a selected device. Inside submit, a command group is created through the handler. The _task function defines a kernel containing one logical task. Notice that kernel execution may be asynchronous. Calling wait ensures that the submitted work is completed before the application continues beyond a point where the result is required. Later, we will replace _task with parallel_for to launch many work items. A typical SYCL workflow begins by identifying the part of the problem suitable for parallel execution. The program then discovers or selects a device and constructs a queue associated with it. The required data must be made available to the device through unified shared memory or buffers and accessors. The host then submits a kernel to the queue. After execution, the program synchronizes where necessary, retrieves or accesses the results, and verifies correctness. Finally, performance is measured. This last step is important. Successful execution only demonstrates functional correctness, not that the parallel implementation is efficient.